Well, when we knew Carl was coming, and I talked to Quinn about this, and I said, I'll warn Carl, it's Friday afternoon before spring break, and Quinn and I said, well, we go.
Yeah, I get always the prime speaking times and dates. But there's a search, right? So I appreciate a lot of people are going to be very tired after all the talks from the search.
I always said the searches are over, but they're not. Should have one more. One more person for the last search.
Yeah.
So yeah, I don't know how much it counts. So we've got like 2.5 searches.
Yeah, it's a little less intense. All right, well, welcome everyone. Thanks for coming out. You could be out on the beach today enjoying your spring break, or getting pelted by snow outside. So today we're very happy to have we'll call this a pop-up colloquium. Maybe that's the trendy thing to do, pop-up events. And so Dr. Carl Mummert, who some of you may know, has agreed to give us a talk today about counting down from infinity and tree 3.
All right, thank you. Thanks for having me down again. It's always nice to visit in Boone. So I'm going to talk about some combinatorial theorems that involve sequences of numbers that grow very, very quickly. So the inspiration for this whole area of math, none of which, except for the very end, none of which I can really take credit for, is this phenomenon. In many cases, you can define functions from the natural numbers to the natural numbers that grow so quickly that you can't even compute their values, right? Even for very small inputs, despite the fact that the sequence itself makes perfect sense as a sequence. And so we'll see a few examples of that, and we'll also see how can this happen, what actually causes it to happen. It's not so bad when you see a picture. So these come up actually in a lot of areas. In combinatorics, they come up in the field of Ramsey theory, and some of these things arguably are part of Ramsey theory. In logic, they come up in computability theory. There's a famous fast-growing function called the busy beaver function that comes up there. But these things also come up in computer science in rewriting theory, right? So you may have, it's very interesting, you may have, in fact they have algorithms where they can prove the algorithm will terminate, but they can't really give you any effective sense of how long it will take, because the proof of termination is non-effective. So they have algorithms, they know that they will eventually halt, but how long will they take? That's another question. And that's because they use these combinatorial methods in the proof that the algorithm will halt. Okay, so we're going to look at 2 of these. The first, Kruskal's theorem and tree of 3, are related to finite trees and graph theory. So I'll show you what they look like, and you'll see what they are. And the second are related to something that I call base infinity numbers, which are like base 10 numbers, except they're in base infinity. Right? So you'll see. Yeah, you can just write them down. It's not so bad. So the first part, the phenomenon comes out of this theorem called Kruskal's theorem. And what it's related to are things that are called labeled finite trees. So a tree is like a graph. You have a root node and some descendants of that and descendants of that. We'll look at pictures. Every tree has a root that it grows from in this setting. And every vertex has a label from some finite alphabet of possible labels, like A, B, C, or 1, 2, 3. They're not just vertices, but they're labeled vertices. So here are some examples. All 3 of these things are labeled trees. The dark border tells you which one is the root. So in the first one, A is the root, or the root is labeled A, and then it has 2 descendants, one labeled B and one labeled A. You can have more descendants, but the tree is going to be finite. It does not have to branch, so that's also a tree. You don't have to use all the labels, so all the possible labels. So all of those, I would say, are labeled trees from the alphabet A, B, C, D. Okay, so what we're actually going to be looking at is trying to fit one tree inside of another tree. That's what we're going to look at. And so that means in particular, we're going to map, every vertex of the first tree is going to map to some vertex of the second tree. And no 2 vertices that are different can map to the same vertex, because we're trying to actually find a copy of one tree inside the other. That's our goal. But there's going to be some rules. The first rule is, every vertex in the first tree has to be mapped to a vertex in the second tree that has the same label. Right? The labels have to match. That's an easy enough one. The second one is a little more complicated to say, but it's not so bad when you look at a picture. So the second one, I'm going to talk through it in the picture, says if you have one node that maps over, like the B maps over, and another node that maps over, their parent, X, has to map to the nearest common ancestor of B and C. It has to map there. Right? So you can't map it somewhere before. So let's look at another picture. So say I want to embed the left tree into the right tree, right? So I need to send each one to something with the same label. So I guess I could do it like that. Right? So this A cannot map to that A because it's not before that thing, or it has to map there. Right? So this is also a tree embedding. Right? So this first tree on the left, I can find a copy of it inside the second tree. Oh, here's one where there's no embedding. I just changed some labels. There's no possible way to embed the first tree into the second one. It can't happen. Right? So if we tried, I guess the B's have to match to B's, right? And the C has to map to a C, right? But then the A is in the wrong place somehow, right? The A should be where the D is, but it's not. It's over there, right? So there's no possible tree embedding between these trees. So you can try them. This, you'd run into this is what you'd have to do, but it's not legal because it doesn't follow the second rule. So some trees can embed into some other trees, and some don't embed into some other trees. That's the phenomenon. Okay, so this is Kruskal's theorem from back 60 years ago now. So suppose you have a long sequence of finite labeled trees, right, where the labels come from the same set. Then what has to happen is there's some tree and some later tree where the first one embeds into the second. But there's another way to say that that makes a little more sense. If you try to make a sequence of finite labeled trees, all with the same labels, and you try to make it so no tree embeds in any later tree, then actually the sequence has to stop eventually. You can't go on forever. It's very much like if you try to make a sequence of natural numbers that never goes up, right? Like eventually you either have to pick the same number twice or you have to stop. But you can't keep going down, right? You can start with 1,000 and go down to 800 and go down to 4, go down to 2, go down to 1, but no matter what you do, you have to stop eventually. And Kruskal's theorem is the same thing, but for finite labeled trees and this type of embedding. If you try to make a sequence where none of them embeds in the next, none of them embeds in any later one, then eventually that sequence has to stop. Okay, so the thing about it is you can actually make arbitrarily long finite sequences, right? So although each particular sequence has to stop, the sequences themselves can be as long as you want. So for example, you could start with this tree on the left. It has n B's and one A, and then just take away one of the B's. Like you know it won't embed in there because you took something away. And then take away another one, right? So you could make a sequence like this, which will have length n, right? And I could have started with any n I want, right? So however long I want this to be, I could start off with 1,000,000 and get 1,000,000 steps. But each particular sequence, once I start it, will eventually come to an end. That's what Kruskal's theorem says, no matter how I start. So there's no maximum length. And what we want to do is to find a way to force there to be a maximum length. Okay, so if you look at this, what went wrong? What went wrong was I could pick the first tree as big as I wanted, and that gave me more and more room, right? So if we add a limit about how many nodes can be in each tree, then we can actually kind of prevent somebody from just starting with an absurd number of nodes, and we can actually get an overall bound on how long the sequences are. So this is what this will say. Suppose we have a sequence of these trees where all the labels come from the same set, and no tree embeds in a later tree, right? And each tree, Tn, doesn't have more than n vertices. So T1 can only have one vertex. T2 can have at most 2. T3 can have at most 3, right? Then in fact, no matter how you make the sequence, overall there's a maximum possible length. And that length is called tree of k, assuming that your set of labels has size k. So you may have heard of this tree number. That's all it is. It says if you make a sequence of trees following these rules, right? So all the labels have to come from A, B, C, D up to K, and no tree can embed in a later tree, and the size of each tree is limited in this way. If you follow the rules, then there's some maximum length of any of these sequences, and that is called tree of K. So let's look at what some of them are. Here's tree of 1. I have one label, and the first tree has one node. If I make any other tree, it'll have to have a label A, and then my first tree will embed into it. So I can't make any more. I'm done. Tree of 1 is 1. It's very nice, easy. OK. How about tree of 2? So again, the first tree has one node. It has to have some label. Say that it's A. The second thing can't use any A's, because if it did, I could stick the first tree inside of it. But it can use 2 B's, right? And then the next thing, well, it can't have an A at all. It can't have a B with another B below it. So all that can actually have is one B, if you think about it. There's no other option. So tree of 2 is actually 3, and that's the longest sequence. Right. So far, tree of 1 is 1. Tree of 2 is 3. So tree of 3, you might think maybe it'll be 8 or 27 or something like, it's not so bad. But it turns out that tree of 3 is absolutely off the charts. So let's start looking at what we can do for tree of 3 rather than tree of 2. So the first tree needs to be something. This time I'm going to call it C, right? And the second one, oh, OK, we'll put 2 A's, right? That'll work. Actually, they shouldn't both be the root, but I think the top one is a little bolder than the bottom one. I don't know. OK, so far I have length 2. So tree 3, I can do that. Now my trees now are growing downward, right? So the root is at the top and the children go down. OK, now I can do that, right? The third tree cannot embed in the fourth because there's not 2 side-by-side B's to put it in, right? And then I can do that, right? If you think about it for a little while, you'll realize that there's no way to embed the T4 into T5 because there's not enough B's below any A. There's nowhere to put it. And T6, I can do that. We're actually just kind of setting ourselves up, right? This is like the first moves in chess where you're just getting the pieces positioned the way you want. We're about to start actually playing. We're just doing the opening right now. But T6 looks like this. And if you check, none of the trees, T1 through T5, embeds in T6. Okay, good. So that's just a summary of what we had, but using shapes instead of letters because it won't fit. All right? So let's look at the next few. For T7, what I'm going to do is I'm going to turn these 2 that are below each other into 3 side by side. And then I'm just going to count down. 3 goes to 2, 2 goes to 1, 1 goes to 0. Then, if I get rid of the top green one, I get to this. And now I'm really going to start playing. Like so far, I've just been setting up. But T12 actually is where I want to be. So again, you could check. None of them embeds in any later one, so I followed the rules so far. But T12, I'm sorry, is exactly what I want to really start making some progress. OK, so here's what we're going to do. For T12, I'm going to trade this blue one for 2 greens, right, in a row. Then I'm going to trade the 2 greens again for 3 greens that aren't in a row, and then count that down to 2 greens that aren't in a row. And then 16 would be 1 green, so 17, I used up those greens. So for T18, I'm going to trade in this green for that many blues, which I can do. And then I'm going to trade in the first blue for 2 greens in a row, right? And then that'll go down to 1 green in a row, 0. Then I'll trade the next blue in for as many greens as I can, legally, and then count down those greens. Then I'll trade in the next blue for as many as I can. So it turns out, when I get to step 3007, I'm down to that, after I traded away all of those as much as I could. And I still have 4 of them to go, right? So the first one, this little piece here, got me 2,990 steps. And the next one's going to get me even more because the trees can be even bigger. So the next one, when I trade this away, how many blues can I put? I can put like thousands of blues, right? And then every one of them I can slowly trade away for more and more trees, right? So that's just one sequence, right? And I'm not even saying, because nobody can write, how long the sequence goes. It turns out we can prove tree of 3 is just enormously large. There's no upper bound for it apart from, well, it's less than tree of 4, right? Like, okay, but apart from that sort of upper bound, there's no upper bound you could write down involving factorials, powers, numbers, numerals. There just is none because it's so big. I haven't proved that, but it's true. It's larger than any number that you could describe in a million words using addition, multiplication, exponentiation, and numbers. So try to make something up. Like take a Google to the Google power, factorial to the Google power, then take a Google to that power, and then square it. Anything you can say like that with a million words will be far smaller than tree of 3. Like it is just the most absurdly large number apart from tree of 4 that you could think of, right? So the sequence, by the way, started 1, 3, and then, right? That's our sequence for tree. And the tree of 4 is just as much bigger than tree of 3 as 3 was to 2, right? So this sequence tree grows really, really fast, right? And that is kind of an issue for me, because I can't tell you what tree of 3 is exactly, because nobody could. So the second thing I want to talk about is something that grows a little slower, base infinity numbers. But let me pause there. Maybe there are questions, or anybody wanted to ask something about tree of 3. Yeah.
Go back to where you had the T, I think it was the previous one.
Yeah.
How does 10 not embed into the right side of 6?
I want one to embed into a later one.
Oh, in a later one.
In a later one, yeah. So 6 does not embed in 10, 10 does not embed in 11, 11 does not embed in 12. Yeah. They definitely can embed in previous ones. That's possible. Right. And this is just one example, by the way. There are longer ones, right? This is just some example to show you just how could it be that it's so large. And the answer is, once you get yourself into the right position, right, you can start doing this trade-off game, right, where you trade one of these for a lot of those, and then each of those you trade for a lot more of something else. So by the time you use up all your resources, you've actually done a lot. Other questions, thoughts? All right, so maybe it gives you a sense how tree of 3 is so big. So base infinity numbers, the tree function grows too fast, right? I mean, it's great. It's a good example of something that grows really fast, but it grows too fast. So let's look at something that grows slower, right? So that means instead of trees, we need to look at something that's simpler, right? But still has similar properties, right? I want the same kind of thing, but more controllable. So that's what led me to think about these base infinity numbers. So what's a base infinity number? Well, it's just an expression like that, which is a bunch of natural numbers in boxes, right? So that one has 4 boxes, 2, 0, 2, 3. The entries can't be negative, but they can be 0. And so you could think of those, they're just like base 10 numbers, except each quote-unquote digit can be any natural number, right? So you could have the number 5,000 in one of the boxes. That would be like a single digit. You could have the number 9 million in one of the boxes, like it's a single digit. Right? But otherwise, they're kind of like numbers, right? You have the digits in a row. And you can order them, right? You can arrange them in order the same way that you would arrange base 10 numbers in order, right? You just order them like they're an odometer, right? So 1102 is less than 2103 because the first 2 is bigger. 11500 is less than 123 because the second 2 is bigger, right? So exactly like an odometer in which each dial could be arbitrarily large, you can order these things. And that's, in many fields, called lexicographic order. It's the same order as a dictionary, actually, right? A comes before B, bat comes before car. All right. So we can actually prove a very similar theorem, like Kruskal's theorem, about base infinity numbers. Suppose you have some sequence of base infinity numbers. At each step, you go down. Then that sequence has to eventually stop. It can't keep going down forever. Right? So this is kind of like Kruskal's theorem. It's like this induction principle for the naturals, right? No matter what natural number you start with, you can't go down forever. right? But you can go down a long time, right? So suppose I start with 1, 0, just an easy starting point, 1, 0. Well, I could go down to 0, 500. That's smaller because the 1 went down, so it doesn't matter what the second digit does. And then I could go down 499 more steps, one at a time, until I get down to 0, 1. And of course, I could put any number there. It doesn't have to be 500. It could be 5,000, 5 million, 5 Google. And that's how long that sequence could run, right? So we actually have a very similar phenomenon, right? I know no matter where I start, eventually I'm going to have to stop. But I can pick different things to start with, which are going to give me longer and longer amounts of time, right? So it's like a game where you know you can't win, but you can decide how long you want to take before you lose, right? So you're like, you know, I don't want to win, but I want to last all day, so we're just going to start with 5,000. Or I don't want to win, but I want to make it all year, so maybe we'll start with 5 million, right? However long I want to take, I can make it take that long, but I can't win, right? I know I'm going to lose. It's just how long is it going to take, right? So that on its own is actually a kind of interesting phenomenon that these things exist, right? Where you know who's going to win, but the other person, they can't win, but they can delay, right? So that's how this is. And it's just like Kruskal's theorem, right? Kruskal's theorem had exactly the same thing. You could start with a big tree, and then it would take a long time to get down to a smaller tree. Okay, so we need to do something, again, to prevent that. So we need to think, how big is a base infinity number? And we're going to use the total of all the digits, quote unquote, as the size. So like 6, 500, the total of that is 506. 2, 1, 2, 3, if I added it up right, adds up to 8, right? It's some count of how big is this number in absolute terms, right? So we're going to call that the total, right? And we have a theorem that's going to be just like our theorem for Kruskal's theorem. It says, say you start with a base infinity number and you make a sequence so that first, you're always going down lexicographically. Second, at step n, the total of an is no more, well, it's going to be n plus the total of the first one, right? So that's why I had to start counting at 0. So A1 can use 1 more, A2 can use 2 more, A3 can use 3 more, and so forth. So we're controlling the growth rate, just like in the tree of 3 sequence, we control the growth rate by saying the tree of stage n has size n or less. And say the sequence, we know where it ends. Say it ends with 0, 1. Then there's actually a maximum length for that sequence, which I'm going to call C, like count or countdown of the initial thing, right? And because I said, because of these, yeah, there is a maximum. This is a theorem. I'm going to call that the count for that number. So you can see how this is actually a very similar method to how tree of 3 was derived from Kruskal's theorem, right? You take one of these theorems that says things eventually have to stop, but we don't know how long. And by controlling the size along the way, you can force there to be an actual maximum, not just arbitrarily long. So let's look at an example. Say I start with just 1, 1. So the limit for what the total is allowed to be at this stage is now 2, because the original one added up to 1, 1. So the next stage, the limit would be 3. The next stage, the limit would be 4, and so forth, right? At every step, my possible limit on the total goes up by 1. So where can I go down to from 1, 1? Well, I don't want to go down too far, like just jump all the way to the end. So what's the least amount I can go down? If you think about it, it's 1, 0, right? But then after that, since my limit is now 4, at the next stage I should go down to 0, 4, because I'm trying to stave off losing as long as I can. And then I'll have to count down after that, right? Once I'm in 0, 4, like the end is in sight, it's just like waiting it out, right? So 0, 3, 0, 2, 0, 1, and eventually I'll be done. So what that says is that the count of that original thing is something. For the second one, say I start with 2, 0. So that means if I try to go down as little as possible, I'm going to go down to 1, 2. Right? I don't have to go down to 1, 1 because my limit at this stage is 3. So I might as well go down to 1, 2 and use my whole limit whenever I can. But then I'm going to have to go down to 1, 1. The difference is now I'm at 1, 1 with a limit of 4, not 1, 1 with a limit of 2. So then I have 1, 0. I get down to 0, 6 instead of 0, 4. And now again, the end is in sight. I have to go 0, 5, 0, 4, 0, 3. So we'll look at 3, 0 next. But let me point out, this means C of 1, 1 is 6 because there's 6 steps. C of 2, 0 is 10 because there's 10 steps. I'm actually counting the number of elements of the sequence. Let's look at 3, 0. So again, the limit starts with 3. If I try to count down, the 3 has to go down to a 2, but I might as well make it 2, 2, because the next thing, they can add up to 4. Then 2, 1 and 2, 0. At the next stage, my limit is 7, so I might as well go down to 1, 6, right? Make it as big as I can. Then 1, 5, 1, 4, 1, 3, 1, 2, 1, 0, with a limit of 13. So then I get 0, 14, and then I can count down all the way. So this should say 3, not 2, right over here. And that says that the count, if I start with 3, 0, the maximum length is 25. So these are much more controllable than tree of 3, right? Like 25 is a lot better than, indescribable, right? So here's a problem, right? Say we want to find a formula for the actual value of C of alpha in terms of the numbers that appear in alpha. So alpha is one of these base infinity numbers. Can I actually just send a formula that just tells you, oh, I don't have to count it out. I can just say this is what it is. So it turns out it's kind of non-trivial, right? It's not easy if I just start with 5, 1, 2, 70 to tell you exactly what that'll be. Now I can program it in a computer, and I did, right? So I can try to run things and see how long they are. And you can kind of see that there's some recursiveness, right? Because I saw like 1, 1 over and over in different places. But what we could do is look at something like, what if there's just one box? Okay, that's pretty easy. What if there's just 2 boxes, right? That's a little less trivial. What if there's 3 boxes? So I've had 2 students work on this as part of their undergrad capstones, right? And it's actually a very interesting project. And one nice thing about it for capstones is you can build up, right? If one person does 2, 2, and did 2 and 3, well, the next person could look at 4, right? But so we got some results, and I'm going to kind of tell you about how they go. So what Samantha showed was, if you count down from K0, ending at 0, 1, just like we said, this is actually the value. So it's 2 to the k plus 2 minus the quantity k plus 4. That's exactly it. So for example, 3, 0, we already said was 25. 4, 0 turns out to be 56. So for 2-digit, quote unquote, for 2 box numbers, it grows like 2 to the n. What about 3 boxes? That was the next question, right? So we already saw that C of 1, 0, 0 is 11, right? So I thought, let's just run it in a computer. Let's see what the next one is. So C of 2, 0, 0 turns out to be 65,000, right? So this, by the way, is another useful application of math, right? Math is applied in many ways. You can use math to win money at the bar. You show somebody how to do it for 1, 0, 0, and you bet them they can't do 2, 0, 0. And they'll say, of course I can do 2, 0, 0. How hard can it be? And then, after a couple hours, you leave with your money. So, right, 2, 0, 0 is 65,530. That's what it is. 3, 0, 0 is about 10 to the 19,000, right? And just for comparison, the number of atoms in the universe, people believe, is less than 10 to the 100, right? So just how long does it take to count down from 3, 0, 0 to 0, 0, 1? If you try to do it as long as you can, the answer is there's more steps than there are atoms in the universe. So you know you're going to win that bet. It's the best type of bet, right? So this grows much more quickly, right? And that's the phenomenon that we see, right? It's like the sequence is not so hard to define, right? The first elements aren't so bad, but it grows really fast. So let me show you why 3, 0, 0 is so long, right? Because you might not even believe me. How could it possibly be that long when 1, 0, 0 was 11, right? So let's see what happens. So 3, 0, 0, the limit is 3. So if I try to go down, if you think about it, the next thing I could possibly go to is 2, 2, 0 with a limit of 4. There's nothing in between that would work. Then I'll count down to 2, 1, 2 with a limit of 5, and then 2, 1, 1 and 2, 1, 0. Now I'm down to 2, 0, 6. Eventually I get down to 2, 0, 0 with a limit of 14. So I might as well go down to 1, 14, 0. That adds up to 15, so I'm still good. Now, from 1, 14, 0, I can go down to 1, 13, 2. And now, again, I'm in a position where I'm ready to really play, right? So 1, 13, 2, I count down to 1, 13, 0. And then I go down to 1, 12, 6. And I count down to 1, 12, 0. And then I get 1, 11, 14. And then I count down to 1, 11, 0. And then I get 1, 10, 30. And then I count down to 1, 10, 0. And I get 1, 9, 62. And after 135 steps, I get down to 1, 8, 126. And after 262, I get down to 1, 7, 254. So you can start to see how this is going to blow up, right? So one thing that's interesting, let's look at the pattern in the last digit. So this is a 30, and this is a 62, and I think we have some time. This is a 62, and this is a 126. So what's happening there? Like, what's that pattern? It like doubles, and you add 2, I think, if we want to really be exact about it. Right? Doubles, and you add 2. So I could tell you, right, without actually having to count them, the next one's going to be 508, and the next one's going to be 1016. And basically, I'm going to get 2 to the 7, right, because I'm going to double it 7 times, right? So I'm going to get 2 to the 7 times this, or if I go all the way back up, I'm going to get about 2 to the 14, right, just to get down to 100. At which point, I'll be able to get rid of the first 1, and I'll get something enormous in the second digit, right? And then I'll get to play this game all over again, right? So that's how this thing ends up giving you such a long sequence, right? Not because each part is so long, but because like each part is twice as long as the previous part, right? And somehow by the time I'm set up, I get to do that, well, 14 times before I even get rid of the first 1. And after I get rid of the first 1, I'm going to have some enormous number, like 2 to the 14, which I will again get to raise to a huge power. Right? So I'm not going to show you an exact formula, but I'll give you some bounds. It turns out that for 3 boxes, it's very closely related to an operation you may or may not have seen called tetration. So everybody knows 2 to the n is 2 times 2 to the n minus 1, right? So you could write that the other way. 2 to the 0 is 1. And if I add 1 to the exponent, then I need to multiply by 2, right? That's a recursive way of talking about 2 to the n. And there's a notation in computer science called Knuth's up arrow notation. Instead of writing a superscript, you just write an arrow, right? But it means the same thing, right? It's just we don't have a symbol for powers, so he made up one. It's an up arrow. Okay, so tetration is the same thing, except instead of multiplying, you put a power at each step, right? So you start with 1, and then you take 2 to that power, 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 instead of multiplying by 2. So let's look at what that means. So 2 tetration 0 is 1. That's the starting case. Then I need to take 2 to the 1, and I'll get 2. I need to take 2 squared to get 4. 2 to the 4th is 16. That's 2 double up arrow 3. Then 2 to the 16 is this. And 2 to the 5th is about 10,000, 10 to the power 19,729, which we already saw, right? It came up in my experimental evidence for 300, right? So in general, right, if you want to write them down with dots, 2 to the n, you write the dots horizontally, and tetration, you write the dots diagonally, right? That's tetration, right? So it doesn't come up much if you're working in college algebra, but it does come up in combinatorics. This is one place. Like it just came up as part of this sequence, right? So what you can prove, for example, is that if you start with k00, then the length of that sequence will be at least, will be bigger than 2 to the 2 to the 2 to the 2 to the 2, k plus 1 times, right? That's fast, right? I mean, that grows way faster than exponentiation. It grows way faster than factorials, right? It's pretty fast growing, and it's just 3 boxes, right? So you might guess what should happen when you have 4 boxes. I have a guess, which is we should move up to whatever's next after tetration, right? And that is, in fact, what's going to happen, right? So as the number of boxes goes up, this function is going, the length of the C function we're going to need things that grow even faster and faster. But because of the way this grows, it actually is going to match up with this sequence of hyperoperations. So you had multiplication, powers, tetration. There's another one after that, another one after that. You know, the next one is 3 arrows. The next one is 4 arrows. And this sequence actually matches up very tightly against that rate of growth, like the rate of growth of these hyperoperations. So that's an interesting phenomenon, and I'm glad you listened. Let me talk to you about it. Thanks a lot. I can take questions, and I do have an encore. So you can decide which one you want.
So if we do like what, n boxes with n, so we get to
Yeah, basically. So yeah, so there's a similar thing that grows in this way where you have these levels, each of which grows faster than the previous one, called the Ackermann function. And this is very tightly tied to that, except that this comes from a nice thing about counting down sequences, whereas the Ackermann function comes from some ugly recursive formula. Yeah. Oh no, I think that, yeah. I mean, I think it's great, but you know, the nice thing I do think about base infinity numbers is that everyone can write down some numbers in boxes, right? Like there's nobody who can come to this talk plausibly who cannot write down them and actually count things down. They're very nice to work with. Better than trees.
So is there a firm understanding, right? Because it seems like, right, as you increase these number of boxes,
Yeah.
somewhere in your sequence you kind of return to something you looked at earlier. The difference is that your maximum allowable
Yes.
count is larger now. So and maybe you have like looked at these, but instead of say starting at level n and working up each time, starting at some arbitrary thing and working up one each time.
So you're exactly right. So that when you actually solve these problems, when you're actually getting formulas like, let me find this formula. This one. When you actually find this, you actually do it by computing a different function, which is starting at alpha with a certain limit. And you set up a recurrence relation for that function. Because if you look at these things, you can start to see recurrence relations. Then you solve the recurrence, and that's how you get this thing. But then, in the final theorem, this is something that also happens pretty often, you forget that you had that extra parameter, and you just look at, what if I start with the total of alpha in there, the least possible? And that gives you this theorem. But yet, to actually work it out, you have to consider an extra parameter along the way, which is the starting limit. Yeah.
The approximate one, is that a computational estimate, or is that just sort of 200 being approximate?
Oh.
These are exact numbers.
No, okay, this one is exact. This is a computational estimate, but I did run it and get an exact number. I just rounded it here. The thing is, because it's recursive, you can kind of, you can compute how long various steps will take rather than counting them. And in that way, you can actually figure out how large it is without counting every step. So even though nobody could possibly run a computer for that many iterations, right? Even if you ran one every, ran a Google on them every second, you'll never get that many to run. But by skipping over lots of them and just saying, oh, here's another billion, here's another trillion, here's another one of these, and working with an arbitrary precision computing environment, you can nevertheless produce a count of how many there are without actually counting them. So that's what I had to do there. Yeah. If you move up another one, even that's not going to be feasible. Right? You'll start to run out of memory. But for this one, you could do it. I think 400 I could not run without thinking more. Right, well, maybe let me show you one more thing for an encore. So I told you about tree of 3, and I told you about these base infinity numbers. What's a relationship, right? I mean, obviously, tree of 3 is way bigger because I told you it was. But can you get like a combinatorial proof, right? Can you like directly show a relationship between these two things? And the answer is you can. Like you can directly show combinatorially that the base infinity sequence gives you a lower bound for the tree sequence. So let's see how that works. So let's embed C of 100 into tree of 3. So we'll just do it like this, right? Here's 1, 0, 0. Here's 2, 0, 2, 0. Here's 1, well, I'm sorry, 0, 1, 2, 0, 1, 1, 0, 1, 0, 0, 0, 6, 0, 0, 5, 0, 0, 4. Each of those is a tree from an alphabet of 3 options, right? Red circle, blue circle, or green diamond. No tree embeds in a later tree because of the way I constructed it, right? So definitely, C of 1, 0, 0 has got to be a lower bound for tree of 3, right? Even without counting either one of them, right? Just combinatorially. And this is one nice thing about combinatorial proofs, right? You don't have to count the 2 sides to know that one of them is a lower bound than the other one. You don't need a formula, because you can directly embed one problem into the other, right? So if you generalize that, what you'll get is, tree of n in general is greater than or equal to C of something that starts with a 1 and has n boxes. Is that a good bound? No. But does it show that tree of 3 grows pretty fast? Yes, right? But it also shows you how you can get these relationships between principles, even without formulas, just by thinking about how could I turn an instance of one principle into an instance of the other, right? How can I turn a sequence of base infinity numbers into a bunch of trees? Yeah. Thank you.